All right. Last time, we talked about steady state and non steady state diffusion, and we mentioned multiple times the diffusion coefficient or diffusivity, D. And today, in this module, we're going to talk a little bit more about that term. All right. So, the diffusion coefficient, D, or as it's sometimes known, diffusivity, is a function of temperature. So the last example we worked in the previous lecture, uh, we uh, we gave you the diffusivity for carbon and iron at a specific temperature, but we can also calculate the diffusivity from that function of temperature. And so this is the expression of diffusivity or diffusion coefficient as a function of temperature. And we see that we have another term, D naught, which is really doesn't have an interesting name or anything. It's just the pre-exponential term, sometimes called the frequency factor, but you can just call it D naught. It has the same units as diffusivity, so meter squared per second, so area per second. And then it's multiplied by the exponential, so exp again. And in that, we see the minus qd over RT. So the qd term is what we call activation energy for diffusion. So how much energy it takes to move an atom. And that has units of energy per atom or per mole of atoms. And then we have R and T. R is the gas constant, and that's 8.314 joules per mole K. And you also can have that in EV per atom per K. It really just depends on what problem you're working. And then again, we have temperature, and that's absolute temperature, and the units have to be K to cancel out. So it has to be on the absolute scale. So you might remember a similar form when we talked about the Arrhenius equation in a previous chapter. And you'll notice it has the similar form, right? We have an activation energy over temperature, and this is all exponential, right? So it's a similar type of expression, and that's what we see. And this tells us that just like the vacancy concentration in the previous chapter, diffusivity is a strong function of temperature in the same way, right? So diffusivity will go up with temperature, just like the concentration of vacancy goes up with temperature. So that's a similar Arrhenius type of expression. So strong function of temperature, increasing temperature gives increasing diffusivity, and therefore diffusion speeds up at higher temperatures. Again, here's the kind of the similarity showing you the Arrhenius relationship. So if we take the natural log of both sides, and then we plot the natural log of diffusivity over one, and then versus 1 over t, we see that the slope is related to the activation barrier, the q over r term. So that's, again, giving us the linearization of this exponential, which is the Arrhenius relationship. And so if we could quantify the diffusivity as a function of temperature, then we can calculate the activation energy for this term. All right, so the diffusing species, along with the material it's diffusing in, will vary this diffusivity. So here is a table from our book that gives the diffusing species. So we see carbon and nitrogen, but also iron in, these are all examples of in iron. So either the structure, so you see it also depends on the structure. And so with that, it gives us the D naught and the QD, which allow us to calculate diffusivity at any temperature as long as it's specified for any of these different situations. And so the other thing to keep in mind is that in the first cases here, this is interstitial diffusion. So carbon or nitrogen are in the interstitial sites of iron, either BCC or FCC. Whereas in this case, these self-diffusion, we're looking at the diffusion of iron in either iron in the BCC form or FCC form. So again, I mentioned diffusivity is a strong function of temperature, and so these are the Arrhenius plots for different diffusing species in different metals. And so we have the diffusion coefficient here, and this is on the log scale, and then we have reciprocal of temperature here, and so temperature is actually increasing as we go from right to left. And so all of this shows that diffusivity or diffusion coefficient goes up with increasing temperatures, and it shows the relative position of all of them. Right, so the higher diffusion coefficient, the faster the diffusion would be. So if we compare, we see that carbon diffuses more in alpha than gamma iron. And this could make sense. We had a previous exam question talking about the different structures, right? Alpha iron, that's the BCC form. Gamma iron is the FCC form. So carbon can't move as quickly in gamma because the FCC structure is more closely packed, and so it's harder for the interstitial ions to move. And so this kind of just shows some of the variations here. And we also see that, you know, interstitial diffusion in iron is much faster than self-diffusion in iron, which is down here. So that's just kind of showing you what happens with various combinations that we see. But again, it's a strong function of temperature, so that's why we see it increase from right to left. And it's linear in this case because this is an Arrhenius plot. And again, you're just looking at various combinations of interstitial or self-diffusion for those materials.